Hello, this is Mrs. Ringrose, and we're back at it again to continue our knowledge on exponential functions and its inverse function, the logarithmic function. So you probably are still asking yourself why? Why do we need exponential functions? And then, of course, that begs the question, why do we even need to know about logarithmic functions? Well, the logarithmic function is the inverse function, and as I've said before in class, every function is going to need an inverse so that we can then solve and make predictions about our world. So this first activity that I posted here, we actually are not going to do it because I know that you guys know the answer. It's pretty straightforward. If you're offered a job where you're going to earn 2 pennies on the first day and then every day your earnings double, basically the question is it a good deal? So you can see from the table that was started for you that by the 9th day, you're making $5. And for a whole day's worth of work, that's not a lot. But if you continue the table, then you can see that your earnings are going to get pretty big pretty fast. If we fast forward to a bigger table and we try to solve for the 30th day, we could go ahead and just do it by hand and double every day and figure that out. That's probably not very difficult to do. Or you can write an equation. So I had you doing that before. So a function for this one might be that f of x equals, let's see, we started with 2 pennies, so my initial value goes here. And then I have a base, and the base is going to be how much it's increasing. So I know it's doubling, so I'm going to put a 2 there, because when I times it by 2, that doubles the amount. And it's doubling every day, which is x, so I don't have to transform the input at all. And so this could be a good function to model this equation or situation. So now what I want to do is plug in 30 to find out this amount right here. All right, so let's go ahead and do that together on the calculator. All right, so if we put this into the calculator correctly, then we are going to find out that we have 214,74836. So that's a lot of money right there, right? And that's just what you're earning on the 30th day. Like if you want to talk about your total earnings, then you can go ahead and add all those together, and that's going to be a lot of money. So yes, that is a good deal. But what if the problem asked you to find out on which day you earn 50 million, or something along those lines? So instead of having to sit there and make a table for so many days, we can find a way to solve it. And again, some of you guys have already been doing this because we did some of the exponential stuff already. We can just use a graphing calculator and see where it comes out on the table. That's a valid method. But we're also going to learn how to use logarithms to solve equations as well. But before we get thrown into logarithms, let's take a step back and recognize that you don't need to use a log to solve every single exponential equation, right? So the first exponential equation says that 2 raised to some power equals 2 to the third. Well, since the base is the same, right? So notice the base is the same, right? That's super important. Then what I can do actually is just set the exponents equal to each other. So it's kind of like the bases cancel out, right? So I find out that x equals 3. So that one's pretty easy. All right, what about number b? So number b, it says 2 raised to some power equals 2, and there's no power there. Well, I know that when I don't have a power, it's actually to the power 1. So now they do have the same base. So now I can say x equals 1. All right, so that was pretty easy. All right, what about c? So again, you don't need to jump to your calculator just yet. I can make 16 look like some number that is a power 2 raised, I'm sorry, not a power 2, but a base 2 raised to a power, right? Because I know 16 is 2 to the 4th, because I have all my powers memorized of 2. So now I can rewrite this equation as 2 to the x equals 2 to the 4th. And now my bases cancel out, and I'm left with x equals 4. All right, what about d? So again, what I could do is I could say, first I can add 64 to both sides. That might be a good step algebraically. So now I have 2 to the x equals 64. And I'm again going to think about how can I rewrite 64 so that it's expressed as 2 to a power. So 2 to the x equals 2 to the 6. And then my bases cancel out and I'm left with x equals 6. Yay. This isn't so bad, right? All right, so now I'm going to look at some more examples. And, if you want to pause me at this point and try to do the rest on your own, then that would be super. But if you're still kind of clueless, feel free to follow along. So next, I have one that's very similar. So my equation is now 2 to the x equals 1. And I have to think to myself, how can I raise 2 to a power so that it equals 1? And that's simple because 2 to the 0 power is going to be the same as 1. So I'm left with x equals 0. All right, f is a little bit different because you can kind of see this as two ways. My first inclination is to get the 64 to look like 2 raised to a power. So now I have 2 cubed x equals 2 to the 6th. And then I can set 3x equals 6. And then I find out the x equals 2. Or I can think of that 2 cubed part first, and I can rewrite that as 8 to the x, and I can change 64 to 8 squared. So x equals 2 either way. I guess it's how your brain is working at the moment, how you want to attack that problem. But again, we didn't have to use logarithms, so don't just take out the big guns every single time. And then finally, I have an addition expression right there in my exponent, but that's okay. We're going to solve this the same way. I can rewrite 32 as 2 to the 5th. So then my bases cancel out, and x plus 1 equals 5, which leaves me x equals 4. All right, so I'm going to write down any questions that you may have for me, but these are pretty much, what I'm expecting to be able to do. All right, so this may look like a bit of the same, but I just kind of ramped them up a little bit because I want to make sure that you're really being thoughtful on how to change some of these bases. So the first one's easy, right? The 5's cancel out. And so then I can rewrite this as 2x equals 4 plus x. So then I can solve this, and I get x equals 4, I think, right? This next one, so this was from the previous lesson. How do I make this look like 2 to a power? Well, I know 2 cubed is 8, but this is the reciprocal of 2 cubed. So I'm going to rewrite this as 2 to the negative 3. And then once I have that, these 2's can cancel out, and x equals negative 3. All right, the next one is very similar to 2 of the ones I did in the previous page. So I'll let you try this one on your own. And it looks like x is going to be negative 1/2, if I'm doing that correctly in my head. And then finally, I've got this one. Now, the square root of 27 is not a whole number. It's not an integer. So probably what I would do is I would try to rewrite this as 9 to a power, or maybe even change the 9 to 3. Like this one could take a couple extra steps, right? So this one can be written as 3 squared. But when you take the square, that's going to end up getting distributed to that expression that's in the exponent. So make sure we write it like that. And then 27 is actually 3 cubed. So I have the square root of 3 cubed. Well, and then I know what the square root can also be written as a rational exponent. So I can rewrite that as 27 to the 1/2. So that means that radical 27 is really 3 to the 3/2. So I hope you remember your Algebra 2 training. And then now I have the same base. So I'm going to say 2x plus 1 equals 3 over 2. And then you're welcome to solve that any way that you want to. All right, so hopefully that was some help. Just have a couple more examples to go through, and then you're on your own with your homework. So some additional log expressions that you can solve, or equations, I should say. That first one, log x equals 3, this means log base 10, right? When there's nothing there, we call it the common log. So what is that really asking? If you want to rewrite it as an exponent notation, you can, right? Because this is saying 10 to the third power gives me what number? And that's where your x is. And obviously, that's 1,000. And then I have another one, log base 2 of x equals 5. So again, my base is 2 raised to the 5th power gives me what answer? And that answer is going to be 32. And then finally, you might see some things that look like this. Whenever you have a log base and this is the same as the base of your expression, like for instance, natural log is base e, and then we see the e. So whenever you're taking the log of itself, right? So any of these kind of examples, they basically cancel each other out because they're inverse operations, right? What number do I have to raise e2 to get e? What number do I have to raise 2 to get 2? So when you simplify things that look like this, you can actually just cross those out if they're the same, and my answer is the exponent. I cancel this out, and my answer is the 4. And we're going to get more into that later with the properties, but I just wanted to give you a heads up. Okay, so what was it that you were supposed to learn? Check off the things that you can do from this video, or maybe some of the stuff you already knew how to do, is be able to solve exponential equations using same bases, and be able to simplify exponential and logarithmic expressions. So there's no Google Classroom assignment. If you have questions on a particular example, please reach out to me. Just look for the homework 6.3.2 that will be assigned on Pearson, and please have it done before Friday so I can see that you're doing stuff. All right, thank you and have a great day.